Greetings, everybody. Let's look at the last part of this ladder problem. Okay, and I say that because at this point in time, I've already made videos to address parts A and B, and I want to look at part C. So here's how part C goes. The situation was, as has already been described in parts A and B, that we have a ladder leaning against a wall, making contact with the floor and the wall, and the base of the ladder slides out, and we presume the top slides down. Okay, and the ladder with its points of contact to the wall and the floor make a right triangle. And if I'm told that the base of the ladder is sliding away at 7 feet per second, then I can say if this distance is x, then dx over dt is 7 feet per second. For you to say that the base of the ladder slides out at 7 feet per second, and for this measurement, this distance to be x, then you're telling me the derivative of x with respect to time is 7 feet per second. We found also in part A that the top of the ladder slides down at 24 feet per second, making dy over dt negative 24 feet per second. Negative because the y aspect of this triangle is getting smaller. Maybe the top of the ladder is moving through space at 25 or 24 feet per second. But as far as this triangle goes, y is getting smaller by 24 feet for every second. Okay, so for part C, asking about how this angle changes, I could say, well, it's going to get smaller. But it is changing in time. It has to. If this gets bigger with time and that gets smaller with time, then the angle also appears to get smaller in time. So I know that there's an answer to that. As far as the tool I would use to figure it out, it's the derivative d theta over dt. So if I can get d theta over dt to show up in my equations, then I'll be able to tell you what it is. Okay. The extra condition that we have on this is that all of these questions were to be answered at the moment when the base of the ladder making contact with the floor is 24 feet from the wall. Okay, so that's the condition that we're given to answer this question. Now, let's do this. I think that based on my experience with the other parts of this problem and generally knowing how these work, we'll need to know what y is. Like, so say x is 24. I think we probably need to know what y is at that same moment. Okay, so if the ladder is 25 feet and the base happens to be 24 feet away from the wall, then I can solve for y, the vertical aspect there, with the Pythagorean theorem, and I'll get that y is equal to 7. So I did that when I solved part A. Okay, probably part B. Okay, all right. So okay, let's do this. Let's solve it now. I think I have all the information I need. Now, the procedure went like this. Start with a true equation that relates to variables of interest. So what I mean by that is there an equation that relates what I'm looking for, theta? I want to know how theta is changing in time. And some equation that relates that to x and or y. Okay. And quick look at this triangle. I can say, yeah, there's an equation that does that. Here's one. Cosine of theta is x over 25. That's a true equation about this situation. It relates the x, which I know something about. I know dx over dt, and I know x is 24. And theta, which is something I'm interested in. Okay, so that's always the starting point. Start with a true equation that relates to variables of interest. That true equation could be algebra, geometry, something like that. It won't be calculus, though. Step 2, take the derivative with respect to time using applicable rules. Okay, so all right, I've got my equation. I need to take the derivative with respect to t time. Of this equation, cosine theta is x over 25. What I would get is, well, the derivative of cosine, I got to use the rules as they're appropriate. The derivative of cosine is minus sine, but then times d theta over dt. I'll say more about that in a minute. Because you might think, why don't you just say that the derivative of cosine is minus sine? Why do you follow the d theta over dt? So I'll say more about that in a second. The derivative of x over 25 is 1 over 25. 1 over 25 is the coefficient of the x there, times dx over dt. So same thing there. Why follow it with dx over dt? Why not just say the derivative of 1 over 25 times x is 1 over 25? Why follow it with dx over dt? So real quick, let's address that, then we'll continue with this problem. So yeah, why do we say that? Why do we say the derivative with respect to t of cosine theta is minus sine theta, but then times d theta over dt? Alternately, you could say, why isn't it just that the derivative with respect to t of cosine theta is minus sine theta? Why don't we say that? And the answer is because theta there is a function of time, and as a result, we have to use the chain rule. Theta is, we're not taking the derivative here with respect to theta, assuming that theta is the foundational independent variable. That theta is a function of its own that somehow depends on time. All right? So that's why we got to follow it up like that. If you want an analogy, then you can think of it like this. See, I said, well, we do it like this because theta is a function of time and we're using the chain rule essentially. It's like this one. What's the derivative with respect to x of cosine of x squared? Well, it'd be negative sine of x squared times 2x. Why do you follow it with the 2x? Well, the chain rule necessitates that we do that. Okay. The chain rule for this is that we say the derivative of cosine of x squared is minus sine of x squared times the derivative of x squared, whatever that is, and it's 2x. Okay. So here we'd say the derivative with respect to t of cosine theta is minus sine theta, then times whatever the derivative of theta is with respect to t. Okay, so we're putting that there because the chain rule necessitates it be there. Ultimately, though, it gives us a way to solve for d theta over dt. Something similar is why on the other side I say the derivative with respect to t of x over 25 is 1 over 25 then times dx over dt. It's the chain rule all over again. It's the fact that x is not just x is a function of theta. Okay? All right. So now at this point, we've done two. We took the derivative with respect to time using the rules that are applicable and correct. The third part is we'll solve for whatever the derivative is that we want. Okay? In this case, that is d theta over dt. But we're going to have to use all the information that is known and relevant. So see this right there? A d theta over dt is just sitting right there in it as if I could solve for it. To fully solve for it, all other aspects of this equation would have to become known. So to solve for d theta over dt, I'm going to have to know what negative sine theta is. And I'm going to have to know what dx over dt is. So let's see if we can figure that out. First, dx over dt was just given in the statement of the problem. It's 7. It was said that the base of the ladder is sliding outward 7 feet per second. So that we just know. I don't have to do any work to find it. I just have to recognize it's what I need right here. What about minus sine theta? Is there some way to say what that is? Because unless I can tell you what minus sine theta is, then there's no way to solve definitively for d theta over dt, and that's what I want. I want to know how fast that angle is collapsing as the base of the ladder slides out. So, well, look, here's what we know. We know there's the angle. We know the ladder's 25 feet. We know we're talking about this in the instant that the base of the ladder is 24 feet outward. That makes the top of the ladder 7 feet upward. So I've got all that. That's enough for me to tell you what negative sine theta is. See, there's theta. What's sine of an angle in a right triangle? It's opposite over hypotenuse. So by extension here, I know that sine theta is 7 over 25. So see, I'll put that in there for sine theta. Now, when I do that, notice, in step 3 here, using all the known information as I need to, that leaves only the thing I'm trying to solve for. That leaves d theta over dt. But you'll have to do that. You'll have to, reveal all unknowns here until the only thing that's left is what you're trying to solve for. And that's where I am at this point. So I can solve for d theta over dt by multiplying both sides by negative 25 over 7. I'll get this. That gives me -1, and my default units are angular units over time units, but the angular units are radians, okay? What this will give you as the initial answer is going to be radians per second. So if I get -1, that's -1 radians per second. So that's how fast that angle is collapsing out of this triangle as the base slides that way and the top slides this way. I think degrees per second is a little more natural. And so I'll give you an alternate answer. I'll say, well, a radian is 180 over pi degrees. So I could say, since 180 over pi is about 57.3, I could say, well, that angle is collapsing by about 57.3 degrees per second. Okay, so you could say it that way. In the question on my math lab, it's in radians per second, so we'll say -1. Okay, all right, now real quick, I want to address the issue of, is this the only way? This first part, start with a true equation. There are other true equations about this situation that I could start with here in step 1. Okay, like I just want a true equation that relates theta to x and or y. So what about these? We could start with sine theta is y over 25. That would work. Isn't it true? Let's see. Sine of that angle is this side over that side. Yep. So if we do that, that's a starting point. Take the derivative. We get something very much similar in our work to the other problem, and we get the same answer. Okay. Is there another way? Is there another true equation? Tangent of theta is y over x. That could be another starting point. All right. So there's a third way to do it. So I could say tangent theta is y over x. Take the derivative with respect to time of that. The maybe part about doing it this way that's a little more difficult is we'd have to use the quotient rule on that right-hand side. We would get dy over dt times x minus dx over dt times y. That's just the quotient rule over x squared. Putting in our known values, we'll still get -1 radians per second. We get the same answer. So that's the way calculus goes. There might be several ways to set up one problem. Okay. All right. So just know that that's true. Know that if you work the assignment, you might think of something different than me. And that's probably okay, all right, as long as all your reasoning is correct along the way. But other than that, maybe just focus on the broad outline and making sure that you get the true equation, that you understand the considerations for getting that part, and that you can recognize all the applicable rules for derivatives that you need to use along the way.